the differential forms of the fundamental laws, tutorial number 3. Consider two long, horizontal, parallel plates with a viscous incompressible fluid placed between them. The two plates move with two different constant velocities. There is no pressure gradient and the only body force is due to the weight. Starting with the Navier-Stokes equation, determine an expression for the velocity profile for laminar flow between the two plates. Here you could imagine that we have two plates like this, and between these two plates there is a fluid, and the gap here is mentioned as h. We take this direction is x and this direction is y axis. However, this plate is not fixed. The bottom plate here is moving from left to right with a velocity v1, and the top plate here moving from right to the left with velocity v2. So starting with a Navier-Stokes equation, as mentioned in this question, we need to determine the velocity profile for laminar flow between two plates, these two plates. We know that the motion of the movement is focused in x direction, so we use Navier-Stokes equation in x direction, and this Navier-Stokes equation is written like this. Then we need to make a few assumptions, so we could simplify our Navier-Stokes equation with our assumption. The first one is we take this calculation as y is one dimension, so the value of v and w will equal to 0 because there are no movement or there are no motion in y and x direction. So we also take the flow is steady state, so the value of du dt is equal to 0. As mentioned in the question, it is incompressible flow, so the value of rho here is constant. It also mentioned in the question the zero pressure gradient means that del P over del X is equal to 0. We assume that it is fully developed flow, means the del U over del X is equal to 0, and because it is a wide channel, means the influence of width of the channel is not very important, so we take del U over del Z is equal to 0. So this is our assumption, and then we will use this assumption to simplify our Navier-Stokes equation. So this is x direction Navier-Stokes equation. This is the long term of Navier-Stokes equation. You may refer this equation in our previous notes. Then we could simplify that the terms here can be simplified as the capital V over dt, and it is equal to 0 because it is a steady state, and then there are no gravity, and also the pressure gradient is 0, and then we simplify this term into mu del square u over del y square. It is because there are no motion of y direction and z direction. So this is the terms of simplified terms from our Navier-Stokes equation based on our assumption as we mentioned previously. So this is the mathematical expression, but this is not the velocity profile. Please remember that in this question we need to derive, or we need to get the velocity profile for that situation. So we need to get the velocity profile here, so we need to solve it by the integration method. So del square u over del y square is equal to 0 now, and then we could split the power of 2 here by write like this, del over del y, del u, del y here, and then we bring the del y here to the left side, so we have 0 times del y equal del u over del y. So the trick is, please remember we want to solve this term by using the integration method. So integral means it can be done with 0. So please do not say that 0 times del y here will equal to 0, because that will ruin your calculation. So please let this term as it is, and then we integrate both sides. So we have the integral 0 del y will become 0, and we will get a constant here. So the integral of 0 dy will have 0 plus constant 1, c1 here. And the integration of del du dy will give us itself. So mean the integral of del u del y will give us del u del y. So we solve this term, we could get c1 is equal to del u over del y. Next, what we next to do is we solve these terms. So we bring the del y here to the left side. So we have del y c1 equal del u. So it can be written like this. So to solve this problem, we again do the integral solution. We integral both sides, so the integration of c1 del y will give c1y, and we could have another constant value here, so we mark as c2. And integral of 1 d del u will give us u. So this is the final terms we get to show the velocity profile of that two plates. So we could write as u equals c1y plus c2. However, c1 and c2 is the constant. So we need to determine the value of this constant, c1 and c2, by using boundary condition. How to determine the boundary condition? So please imagine that we have two plates like this. This is the bottom plate, move from left to right, and then we have a molecule that stick on this surface. This molecule is not moving because there are no slip condition occur at this place at this condition. However, because the plate is moving with a v1 here, we could say that the molecule here is also moving with the velocity of v1. Same condition occur for the top plate here. The molecule is actually stick on the surface of the top plate here. However, this top plate is moving with a v2 velocity, so we could say that this molecule also move with v2 velocity relative to the fluid here. So the boundary condition means we list out the condition that occur at the boundary of the fluid. So in this situation, we could say that the boundary of the fluid is actually at the bottom plates here and also at the top plates here. So we could write down the boundary condition as at y equal to 0. So this is the y direction, and the location here is y equal to 0. The velocity of u, the velocity of this molecule, is equal to v1 because this plate is moving with v1 velocity. And at this condition, at the top plates here, the y is equal to h. And please remember that in the question, it is given that the gap of these two plates is equal to h. So we take the coordinate of y here is y equal to h. And the velocity of the molecule at this coordinate is minus v2. Because the direction of velocity here is reverse direction from the positive direction of x here. So we give as minus v2. What we need to do is we substitute the equation. with the boundary condition. So if we substitute with y equal to 0 and u equal to v1, we could get v1 equal to c2. Then we substitute the boundary condition number 2, which is y equal to h and u is equal to minus v2. We could get it is equal another equation, which is minus v2 equals c1h plus c2. Then we could simplify the terms of c1 here as minus v2 plus v1 over h. Now we get the value of c1 and also the value of c2. Then we substitute in the equation. We could have the final equation become u equal minus v2 plus v1 over hy plus v1. Sometimes people write like this: y equal minus v2 plus v1 over hy plus v1. So the meaning of y here, y in bracket here, is u in the function of y. Please be careful. Sometimes student will take as u times y. It is not u times y, it is just a function. So how to read this one is u in the function of y.